Good deal. And today is the 4th. Okay, let's go through this. And it's the usual stuff. If you have something that's wrong but your work is essentially correct, let me know. And I may give you some partial credit. I may not. We'll see. It depends. All right. Given the surface, f of xy equals xy. What we want to do is set up the double integral that finds the volume underneath the surface over the region in the xy plane. So the only important thing here are the regions in the xy plane. Because all these volumes are going to be set up the same way.
Your work.
My work? Oh, yeah. That was what I was doing to amuse myself while you guys were doing the test.
Doing math?
I give myself math problems to do all the time. Just for laughs. That was just a volume of a sphere intersected by a plane whose height above the xy plane is h, and find the volume of the sphere cut off by the plane.
In terms of h.
Exactly, in terms of h. And the radius of the sphere. It's kind of an interesting problem. But anyhow, so the volume in the first one is, the region is a rectangle, 0 to 2 on the x's. Zero to 1 on the y. So we have our surface above that. The volume is going to be the double integral of our surface. The y's are going to go from 0 to 1. The x's are going to go from 0 to 2. Okay? We had a couple of people getting this one wrong for some reason. I'm not sure what happened there. But that's what the answer would be. Okay? Number 2. The triangle defined by those vertices, let's take a look. 0, 0, 1, 0, and 0, 1. We have a right triangle here. What you're going to have to do is find the equation of this line. That's y equals 1 minus x. The volume, therefore, is the double integral of our surface. Y's are going to go from 0 to 1 minus x, and the x's are going to go from 0 to 1. 0 to 1, yeah. Okay. What's that?
I skipped this one outright, and I put the right one down, and then I circled something different.
Really? Okay, let me keep track of this. Okay, Omar. All right. All righty. Number 3. The triangle defined by, the same triangle, but now we want to put it in reverse order. So the volume in that case is going to be a dx dy. The x's are going to go from left, 0, to right till we hit this. But what we have to do is solve for x. 1 minus y. The y's are going to go from 0 to 1. So the only thing different here is these got switched, and this is a 1 minus y instead of a 1 minus x. It's the only difference there. 4. The quarter circle of that unit circle. Okay. So a unit circle, we want to find the volume underneath that surface over that unit circle. Y's are going to go from bottom to top. The top here, since this is x squared plus y squared equals 1, the y is the square root of 1 minus x squared. And the x's are 0 to 1. All right, how are we doing? Everybody okay? Okay. Number 5. We want to do the same problem, but now with cylindrical coordinates. So it's still a double integral. It's still x and y, but now x is equal to r cosine. Y is r sine. The dy dx is an r dr d theta. The limits of integration are now, since it's a unit circle, the r's are going to go from 0 to 1, and the theta's from 0 to pi over 2. So we end up with an r cubed cosine theta sine theta.
Okay, I have partial on this one.
What do you got there?
Because I made an algebraic error converting one of the values.
Perfect. This is it. Oh, no, it's yeah.
And I made, 'cause I
Yeah,
thought
that's a
that-
1. Oh, I see what you did there. All right, Dave, I'll give you help on that. Okay. How are we doing? Are we okay? Okay. 6 through 10. Given the triangle y equals 1 minus x. Oh, this one's a pain in the neck because we have to actually do the thing out. All right, here we go. I might as well just do it here. We have a density function. That's x. Okay. All right. So first of all, mass. You got to find the mass by taking the double integral of our density function. The y's are going to go from 0 to 1 minus x. The x's will go from 0 to 1. That's 0 to 1. Integrate this, x, y. Substitute in. Well, let's multiply it out. And then integrate it. Get 1/2 minus 1/3, which is 1/6. Okay? So the mass is 1/6. Whoa. Brandon, wait, is that what it is here? I hope. Yeah, okay. Brandon got it wrong. Number 7. Find the moment about the y-axis. Well, the moment about the y is the same integral, except now we need a distance. That distance is equal to x, so we get an x squared. Okay? X density function, x distance, x squared. Integrate x squared with respect to y to get an x squared y. Substitute it in. 0 gives us a 0. Multiply it out. Integrate it. 1/3 minus 1/4 is 1/12. Okay, how are we doing? Everybody doing okay? Okay. All right, you all set? Good deal. Number 8. In number 8, we have to find the moment about the x-axis. And again, it's a double integral. We have our density function of x, and the distance from the x-axis is y. The limits of integration are going to be the same as they have been. And let's do the integral. 0 to 1. X, y squared over 2 dx. We can take the 1/2 out front. Substitute in for the y, the 1 minus x. I would multiply this out. So we're going to have a 1 here, so times x. Middle term is minus 2x, so it's minus 2x squared. Plus x squared times x, x cubed. Okay. We get 1/2 x squared over 2, 2x cubed over 3, x to the 4th over 4. 1/2. We'll have a 1/2 minus a 2/3 plus a 1/4. The people that get this wrong made arithmetic mistakes. I got to tell you, I know. All right, that was pretty much it. All right, so what do we end up with? Well, you got a 1/2, and the LCM of 2, 3, and 4 is 12. So let's go with 12. We get 6 minus 8 plus 3. This is 9 minus 8, 1/12, 1/24. Okay. That's the moment from the x-axis. X bar.
Can
Go.
I have some credit for forgetting to multiply by 1/2?
Let me see. You had the 1/2 in there?
Yeah.
And then you didn't multiply by it? That's partial. Okay. Nice. Moment from the y-axis over the mass. Moment from the y-axis we said was 1/12. The mass we said was 1/6. Bless you. That's 6/12, 1/2. X bar is 1/2. Number 9. 9 is X bar, so that was X bar. Number 10, Y bar. Moment from the x-axis over the mass. 1/24 eeks over the mass of 1/6. That gives you 1/4. Okay. Hopefully that's comprehensible there. So we get 1/4. Any questions on that?
Yeah, can I have some credit?
Oh, you got the same 1/2 problem?
Well, it was, yeah, because, I didn't use the
Yeah,
right
that's-
MX.
Okay. You got it, Tim. Okay. We all set on those? (11 through 15). Given a solid bounded by x plus y plus z, equals 3. What do we have? We have a plane whose intercepts are 3, 0, 0, 0, 3, 0, and 0, 0, 3. Okay, we're concerned about this region in the xy plane. That region in the xy plane has an x-intercept of 3 and a y-intercept of 3. That gives us this line. This is this triangular region here. Okay? So, we got a density function equal to z. And z is pretty dense, so, no, never mind. All right, so, number 11. Okay, find the volume. Just kidding. We have a triple integral.
Recorded.
We have a triple integral here, and what we're going to do is go from bottom to top. So the bottom surface is 0 to the top surface, which is our plane. That's 3 minus x minus y. Bless you. Right here. That's dz, dy, dx. And the y limits are going to go from bottom to top. This line is y equals 3 minus x. And the x's will go from 0 to 3. This triple integral will give us the volume underneath that plane over that triangular region. Okay? 12.
Which is the same as the double integral, 3, 1, 6 minus y.
Exactly right. Exactly right. Which is probably the better way to do the problem. Yeah. The mass, yeah, it's true. Now, when you talk about a mass and we have a density function that's not a constant, then we're forced to use the triple integral. This is where we're going to use the triple integral. We need a z here, but everything else is the same. Okay. And 13 is the moment from the xy plane. And that distance is AZ. We already have AZ density function, and we have another Z, okay, which is a Z squared, therefore. And the limits of integration are again the same. And now the moment from the XZ plane is that distance is a Y, so we're going to have a YZ. And that's what we have. And the moment from the YZ plane, holy mackerel, that distance is X. And everything else is the same. To find X bar, take the moment from the YZ plane and divide it by the mass. Woo! Okay, everybody all set on that one?
For 15.
15, go ahead. Oh, 15. Oh, wait, where's 15? Oh, 15 is this one here. Yes.
Easy. Okay.
You got it? All right, last section, 17 through 20. 17 through 20. We got a top half of the sphere. Okay. Radius 1. Okay. Center of the density function 6 is a constant density function. Okay. Find the triple integral for mass in rectangular. In rectangular, have a density function of 6. Okay. We're going to go from bottom to top. The equation of that hemisphere, the equation of the sphere is equal to this. So the hemisphere is that square root, the positive square root. The y's and x's are going to be determined by this circle down here in the xy plane. And that's a unit circle. The y's will go from 0 to the square root of 1 minus x squared, and the x's will go from 0 to 1. And we have multiply by 4 since we're doing the whole hemisphere, not just that quarter of it in that quadrant. So multiply by 4 as well. Okay? So that gives us the mass of that sphere. Cylindrical coordinates. Okay? Still have a 6. We'll have a dz, but we have an r dr d theta. Okay? The z is going to go from 0 to the square root of 1 minus r squared. That's a minus the quantity x squared plus y squared, which is r squared. The r's are going to go from 0 to 1, and the theta is 0 to pi over 2. Not too bad. 19. Spherical coordinates, 4 times the triple integral. We still have a 6 here, but now we have a rho squared cosine phi, integrating factor. We have a d rho d, and I told you to use d theta first, although it doesn't make any difference at all. Okay. Rhos, sphere, 0 to 1. Thetas, 0 to pi over 2. Phis, 0 to pi over 2. Okay? And that looks to be the easiest of all. Now, I ask you to find the mass. Well, there's a couple of ways of finding the mass. One way to find the mass is to try to integrate in rectangular. Not a good idea. Another way would be to use cylindrical. Not bad because it's pretty simple.
Why
Okay.
cosine, Bruce?
What's that?
Why cosine?
Rho squared, a sine phi.
Ah, all right.
Sorry. I don't know what I was thinking. Good call. Thanks, Denny. All right, rho squared sine phi. Yeah, good call. A third way would be to do this integral, and that wouldn't be too bad either. But a fourth way is the best way of all. It's a constant density. Just use the volume of a sphere. Okay, so the mass of this sphere would be its density function times its volume. It's a hemisphere, so it's 1/2, 4/3 pi r cubed. R is 1. So the answer would be 4 pi. Just cancel out the 6's and get 4 pi. And that's it.
Yeah, can you do the integral out for it?
What? Which integral you want?
The 19 next.
Okay, let's do it. You ready? This is the way to do it. That's the way Janish did it, so that's the way you should have
That's the
done it.
way I tried to do it. And didn't come out really.
Let's do it with the integral. We have 4 times that triple integral of 6 rho squared sine phi d phi d theta d phi d rho d theta d phi 0 to 1, 0 to pi over 2, and 0 pi over 2. Let's do it. So 4 times 0 to pi over 2, 0 to pi over 2. We can take the 6 out too, as far as that goes. We've got rho cubed over 3 sine phi from 0 to 1, d theta d phi. Okay? So 24, 0 to pi over 2, 0 to pi over 2. Substitute in 1, we get 1/3 sine phi. And the 1/3 can come out front. We end up with 8, 0 to pi over 2. The integral of sine phi with respect to theta. Now this is where you got to be careful.
This is probably where I messed up.
Yeah, what's that integral equal to?
Theta.
Theta sine phi.
No, okay, so I'm right. So
Oh, okay, good deal. Because in that context, the phi is a constant. Okay, so you get 8, 0 to pi over 2. Put in pi over 2, the sine of pi over 2 here. And put in 0 to get 0. And then d phi. You okay? You had it substituted in theta. Oh,
Yeah.
all right. So you get 4 pi. Bring this out front. 0 to pi over 2. Sine phi d phi. 4 pi. The integral of sines and negative cosine. 0 to pi over 2. That's equal to 4 pi. Substitute in pi over 2. Cosine pi over 2 is 0. Oh, no,
I
Teddy.
got the 0 because I thought it was just. Oh.
And then minus is plus cosine of 0, which is 1. And you get. I'll give you half credit.
Oh, I was so frustrated. I
Take
couldn't
it easy,
figure it
Ted.
out. I was like, it's 0. How is it?
All right, take it easy. If you did all that out.
Oh, man.
All right, any questions on that one? Yeah. All right, let me just start. Let me tell you what we're going to be doing in the next chapter. In the next chapter, we're going to be doing that. We're going to start off with something like this. The question will be the first question we have to solve is this. Let's suppose you have a wire, okay, a piece of wire, copper wire, whatever, wire, along this path, and this path is described as a function of x. And we want to do the following. We want to find the mass of this wire, okay? The mass of this wire. Let's further suppose that this wire is of changing density. If it were not of changing density, if we had a constant density, we would find the length of the wire. We have, integrals that find length of functions, okay? Back in Calc 2, you had that integral, the square root of 1 plus the derivative squared dx. And in Calc 3, in the beginning of the semester, we did the length in terms of a parameter, where the length of a function between 2 points is that integral of the square root of dx dt squared plus dy dt squared dt. Okay, the parametric form of it. But we did not do anything where the density function is not a constant, it's a varying Okay, the density function is varying. Let's suppose the density function is some function of x and y. Okay, you got a density function that varies. So some function of x and y is our density function, and we still want to find the mass of this wire. Well, we could take a piece of this over an interval here, over a piece of the arc length. Okay. So let's take a piece of the arc length. The mass of that piece of the wire would be approximately equal to its density function, say at the left end point or right end point or some point in that interval, times a delta S. Okay? That would be the mass of that piece of the wire, its density function times an arc length. The total mass of this wire would be equal to the limit, as n goes to infinity, of the sum of all these little pieces. Okay? This is a Riemann sum in terms of S, not X. In effect, what you're doing here, instead of making rectangles to the x-axis like we did in count 2 to find areas where we got a Riemann sum in terms of x, what we're doing here is finding a sum in terms of delta S. It's like we took our rectangles up here on the wire itself and summed up these areas. Because after all, we're taking this piece of arc length times a delta x, a delta y, that's our density function, okay, and summing up all of those along the wire instead of along the x-axis. This is a Riemann sum in terms of S. It's an integral. But we're going to put a little seed on here saying this is not the normal integral along the x-axis. This is an integral that goes along the curve itself. Okay? For C, for that curve itself. Okay? Of our density function, ds. This is called a line integral, unfortunately. It's called a line integral. The original ones went along a line. You had a straight line here, and you integrated along the line, where the delta S was a piece of the line, a little piece of that little segment of the line. But it got generalized to any curve at all, which is what we're concerned about. C for curve, but it's still called a line integral. This is what we're going to be doing next week. We're going to be using these line integrals to calculate, first of all, mass of a wire, but then we're going to end up generalizing these things so that we can find a work done in a variable vector field. And that's what we're going to be doing next week. So there you go. That's just our introduction to what we're going to be doing next week. Okay, see you guys. See ya.
Well, hold on, Bert. Did you just one more second?
Oh,
I started late.
oh,
For the test, or if I could get and then just put down the wrong.
17?
Yeah.
oh man, that's terrible.
Yeah, I know. It's my mistake. I'm sorry.
It's all right.
All right. All set. Oh man, I spent so much time on that last problem. I couldn't understand it. How it could like come out to be.
A zero?
And I tried like all of this crazy stuff. I thought like, maybe I wasn't.
In January.
I didn't think about the fact that